Yeah, so I will start this week's live session because we won't be having enough time to solve the problems. And okay, so just a quick recap of what happened in week 10's lectures. So we saw something about central limit theorem. So that is nothing but when you have many independent random variables like x1, x2, and xn. So all of these are independent and identically distributed. So all these, they could have any distribution. So these would have a mean, like each of these would be having some mean mu and a variance sigma square. So when there are so many such random variables like x1, x2 up to xn, so this could be approximated to a normal distribution with a mean of n mu and a variance of n sigma square. So it follows the central limit theorem in such a way that the summation of the xi, which is given by x bar, minus n mu divided by sigma n root n. So this is the central limit approximation of all these random variables to a normal distribution. So like when it follows this, it's said to follow normal distribution with mean 0 and variance 1, just very similar to a standard normal deviation distribution. Yeah, I hope I'm audible. Yeah, nice slide. Okay. Yeah, it's all fine. Yeah, I think I'll turn off my video because the internet is bad today. But, yeah. Mm. Yeah, so this is how the expression is given. So so if you remember, we saw like for normal distribution, P of uh, x minus mu by sigma, which is Z, like for any random variable, like this follows normal distribution. In a similar way, this one, like the summation of xi up to xn minus n mu by sigma root n. So it follows a distribution where so this becomes the z term here. So like we saw, it could also be expressed as x bar n, this term, the summation term. And yeah, this is always so these are just like examples. So we know that like for distribution, exponential distribution that follows f of x is equal to lambda e power minus lambda x between 0 to infinity. So this has a mean, e of x is 1 by lambda and a variance sigma square is equal to 1 by lambda square. So you just need to apply this in this equation here. So n mu becomes n by lambda because mu is equal to 1 by lambda, and sigma is equal to 1 by lambda and into root 10. So you just apply these for any distribution you have. And when you apply it to a continuous distribution, like Bernoulli or binomial or Poisson distribution, you still use the continuity correction. So you'll have x bar n plus half, which is 0.5, 1 by 2, minus n mu by sigma root n. So you'll have this continuity correction here as well. Yeah, so that was all about central limit theorem, how you can approximate multiple random numbers following separate distributions as a normal distribution. And yeah, this was more of a theory kind of a lecture, lecture 55, needs for drawing statistical inferences. So it's basically you have a large population, and this population might be having some parameter, any parameter called theta. This theta could be either the mu or the standard deviation, whatever parameter you're interested in. The population parameter would be theta, but it's impossible to know this for a very huge population. So in that case, what you do is you just draw random samples from the population and you estimate the parameters. The estimates are called theta hat. So this could be theta 1 hat, this would have theta 2 hat, and this could have theta 3 hat. And what you do here is you take an average of all these estimated parameters. So you basically take theta I hat I1 to n divided by n. So you take a summation, and if this summation this average of all these estimates is equal to theta, it means that it's a good estimate. It's a good, the sample estimates are good estimates for the population. So let's look more into detail about that. So yeah, we learned that T is called a statistic. T is calculated from a sample with values, and we write T of X, and it's called an estimate of theta, which is T hat. So yeah, all of these operations that we do on a random variable, it's called a statistic. Either a summation or anything that you perform on some random variable is called a statistic, which is T. Yeah. So now, so how do you know whether the estimated theta hat is a good estimator for a population? So this is a sample estimate. So how do you say that, oh, this value is good enough for me to apply this to on a population scale? So for this, it needs to have this theta hat needs to have certain characteristics. So it needs to be unbiased, it needs to be efficient, consistent, sufficient, and it should be complete. So all of these characteristics are independent from each other. So because let's say your estimate is unbiased, it doesn't mean that the estimate is efficient. Sometimes a biased estimate would be the most efficient estimate. So yeah, just having a satisfying one of these parameters doesn't mean everything else is satisfied. So each of these are independent on its own. So let's look at unbiased estimators. So by unbiased, we mean that the estimate should be equal to the actual value, or it should be very close to the actual value. So like this is mu, the population mean, and let's say this is your sample mean. So it would be ideal if x bar is equal to mu. The sample mean is equal to your population mean. So that would be the most ideal condition. And if you achieve this, it's called an unbiased estimate. Or if it is very close, like you get so you get x bar is equal to mu minus some value, some bias. So yeah, let's say like this has sorry, your mu is 0.8, but you get your x bar as 0.5. So this means that you have a 0.3 bias. So the bias needs, so that's what is given by this equation. So E of your theta should be theta. So this is what we expect. The sample mean should be equal to population mean. But if not that case, you'll have a bias where this E of theta hat minus theta. So this will be equal to your bias. So when an estimator is unbiased, this bias value will be 0. So because bias is 0, you will have E of theta hat is equal to theta. So here's an example. So this is a population. Population has 3 values, 1, 3, and 5. And the population mean is 3. But let's say you draw random samples from these of size 2. So you can have 1, 3, 1, 5, 3, 5, or 3, 1. Yeah, you can have these possibilities. So when you get 1, 3, the sample mean is 2. When you get 3, 5, sample mean is 4. Like similar. Now when you take an average of all these sample means, so average of 2 plus 4 plus 3 by 3 is equal to 4, 6, 9 by 3 is equal to 3. So the summation of all your average estimates, average summation of this is equal to your population mean. So this is an unbiased estimator. So a simple arithmetic mean is an unbiased estimator of population mean. So that's just a simple example. And yeah, we could just try to solve problems. And yeah, there's one more characteristic. So yeah, your e power, your expectation of x is equal to mu. And yeah, if your random sorry, x bar. So x bar would actually is equal to summation of xi by n. So this would be expectation of this would be equal to mu. And similarly, if your random variable is given by x1 plus x2 by 2, then expectation of this is expectation of the x1 plus expectation of x2 by 2. So it's just additive. So in this case, you'll just have mu, mu. So 2 mu by 2, again, it's equal to mu. Yeah, so we can see how these are applied. And when you have a constant, so you'll basically have 1 by n. So the constant by n, summation of uh, whatever value. So let's say you have x and some constant. So when you add up all these, you'll have n numbers. You'll have n by n into constant. So if constant is equal to 1, this also will be equal to mu, your population mean. The sample estimate will be equal to your population estimate. Mm. Okay, now we saw what an unbiased estimate is. So when the expectation of your estimate is equal to your population theta. And if it's close, there'll be a value called bias. So next we'll see when an estimator is efficient. So an estimator is said to be efficient when the variance is small. So variance is basically the deviation from the actual value. So it is given by this expression. So variance of your estimate theta hat is equal to expectation of theta hat minus expectation of theta hat minus expectation of theta hat, the whole square. So you need to remember this. And yeah, it's called mean squared estimate. So mean squared error. So there's another thing called mean square error. So in this case, so when you derive this expression, you'll have this term. Mean square error is equal to variance of your theta hat plus bias. Bias, the square of your bias. So basically, you need to have variance low, bias also has to be low. So overall, your mean square error also has to be low for the estimator to be efficient. Mm. And also, when you compare two estimates, you compare theta 1 and theta 2. So if you have to choose which estimate is better than the other, if variance of theta 1 is smaller than variance of theta hat, theta hat 2, this means that theta 1 is a better estimate, is a good estimate. Like it is more efficient, more efficient. So how you can calculate this? You can, and also similarly, the MSC, if MSC is lower, that estimate is more efficient. And also to calculate relative efficiency, so efficiency is basically given by, so yeah, efficiency of theta hat is equal to 1 by variance of theta hat. So if you want to calculate efficiency of T2 by T1, it is 1 by variance of T2 divided by 1 by variance of theta 1. So this will go to the numerator. So yeah, it is given by this expression. And similarly for MSC also you have the same expression. So MSC of theta hat 2 by MSC of theta hat 1 is equal to Oh, sorry, I'm doing it the wrong way. Yeah, so relative efficiency of theta 2 hat by theta 1 hat is equal to, so this is directly proportional. So this is also inversely proportional, sorry. MSE has to be low for efficiency to be high. So this is also MSE theta 1 hat by MSE theta 2 hat. And so there's another term called standard error. Sorry. So let's say we have many estimates. Like we have theta 1, theta hat 1, theta hat 2, theta hat 3. So all of these estimates would be having a certain variance. Variance theta hat 1, variance theta hat 2, and variance theta hat 3. So whichever of these is the lowest, it is said to be the most efficient estimator. So this is called like minimum variance unbiased estimator. And there's also something called standard error. So standard error is basically the positive square root of its variance, the variance of the estimator. So variance, you like variance of theta hat. So the square root of this is your standard error. So it's very much similar to standard deviation, which was square root of your variance. But standard error is the square root of your estimated variance. That's why you give a hat, big hat here. Uh, so if you do sampling, not random sample. Cannot see the screen. Harish, can somebody confirm? Can you see the screen? I think there must be a
Yes,
lag.
madam. Yes, madam. Can see, but
There's some outage today. So if somebody else confirm?
madam, yeah, now I can see. I can read.
Sorry. Can you see it now, Abhishek?
Yes, madam.
Hello.
Hello, madam. I can
I
see,
thought.
madam. I can see the screen.
Okay, I'm audible, right? Yeah.
No, you are audible.
Okay, yeah, thank you. It's just showing black screen. Can you just rejoin again? Because I have another device also on, so I could see that screen. And yeah, one of the other students also could see. So yeah, just try rejoining and then let me know. Okay, so let's say there's a normal distribution and you do random sampling from the normal distribution. And then in that case, the randomly sampled random variable from the normal distribution will also follow normal distribution with mean mu and variance like standard deviation sigma square by n. Sorry, variance sigma square by n. So this is the usual normal distribution. But when you sample, it will follow normal distribution with a variance sigma square divided by n. So in this case, standard deviation would be square root of sigma square by n. And this sigma square, not theta square, sigma square. So you will be able to know this only when you know sigma square value. But sigma square is unknown because it is the population variance, right? That is unknown. That is the whole point of this. So in that case, you can estimate the population variance using sample variance, which is given by this formula. now this square root of sigma square by n can also be written as square root of s square by n, which is your sample variance. Yeah, these are just some expressions. Yeah, nothing important here, but yeah, we can look when we solve. And then there was one more parameter called Kramer-Rao lower bound, Kramer-Rao lower bound, which is CRLB. So this value is also a way to measure the efficiency of an estimator. So this follows a bit complicated steps. So you need to so this follows like 4 steps. I think I'll come back to this when we solve a question. So basically, at first you need to calculate the variance of delta x. So delta x is like the differential of x, partial differential of x. So like this, when you write this, it's called the integral of x. And when you write d by dx, it is the differential of x. But when you write delta of delta x, it is the partial differential of x. So yeah, here we have to do like uh 2 times you have to do this partial differential. And then you'll calculate something called I of theta, which is called the Fisher information. So it is given by this formula. It can be either just E of this value, or it can be minus n E of double differentiation of ln it is the log like yeah, logarithm of f of this is basically a function f of x given theta divided by differential of theta square. So yeah, this is called Fisher information. Yeah, we'll get back to this. So I think the last problem I will use this to solve. And how much time do we have? We have an hour. Okay. Now let us solve problems. So this is the first question. Suppose an instructor assumes that a student's final score is the value of a normally distributed random variable. X follows a normal distribution, mu by sigma square. So if the instructor decides to award a grade A to students whose score exceeds, the score has to exceed mu plus 2 sigma. So you need to calculate the proportion of students getting an A grade. So basically you need to calculate P of the probability of X students getting a grade higher than mu plus 2 sigma. So yeah, we know that normal distribution, it follows something like x minus mu by sigma. So this follows a standard normal deviation n 0, 1. So you just have to rearrange this equation. So x is there, mu you bring the side, of the
Madam, excuse
inequality.
me, madam. Madam,
Yeah.
I have one question. Like in the previous assignments, we are getting emails like there was some wrong
Yeah.
this thing and all.
Mm-hmm.
We have already been awarded the marks, the score.
Yeah,
Then
that. Mm-hmm.
what will be the updated this thing, madam?
I'm not sure they'll update it and let you know, but yeah, in our system, in their system, whoever is evaluating, they will update it for themselves, maybe in case they
Like,
didn't share with you the updated scores.
so we should know, no, like how much, what is our score and
Yeah, they'll just make a note of it, of your scores.
But how can we come to know about that? Like
I
there
don't
is
know.
some criteria, no, madam. Like in 8 assignments, you have to. They'll consider best 8 assignments for the
Okay.
final evaluation. So out of 12, you have to take. They'll be taking 8 best assignments.
Uh-huh.
So on what basis? Like what is the criteria? As a
Yeah,
as a
just,
student, I should know my assignment scores. No? So,
but do
like,
you know, like, oh, you don't know the score for any of the assignments, or?
I know, madam. I know,
Oh,
but
then, yeah, that's
the
it.
some questions have been removed, and some
That you can
corrections
just
have been made.
calculate accordingly. You can even like just calculate, remove that from the evaluation, and yeah, but either way, you still have to look at all the assignments with your 8 highest marks, like top 8. That is still
Topic,
gonna be the same. Yeah.
but they should update, no, on the website. Like I'll
That
be
will not
able to.
change anything much. It's just like some relative changes they'll make, and they'll
Okay.
compare with each other, each of your assignments. But yeah, maybe they'll let you know towards the end, like what is your assignment score, like overall assignment score
Okay.
based on 8 assignments. Yeah, I'm not sure how that works though. I
Okay.
can. Yeah, so we had written this P of X should be greater than mu plus 2 sigma. And if you just rearrange this equation, you bring this mu this side, you'll get X minus mu greater than 2 sigma. And again, if you bring this sigma down, like to the denominator, you'll get X minus mu by sigma greater than 2. So yeah, you have got this. So this is basically Z. You have P of Z greater than 2. So now it's just simple, the usual, the standard normal deviation. So you can write with R, you can find P norm to lower tail is equal to false. Why? Because greater than sign. So this will be equal to 1 minus P of Z less than 2, less than equal to 2. So whenever you have a greater than sign, you write lower tail is equal to false. So yeah, if you just do this in your R, you'll get an answer. You'll get something around 0.023. Yeah, you can just try this out. Yeah, this was quite simple, just based on normal distribution. Okay, now the next one. Suppose two fair dice are tossed 1200 times. N is equal to 1200. Let X denote the number of times a total of 8 occurs. So X is like when you roll 2 dice, the sum should be 8. So it can be uh, 2 comma 6. It can be 3 comma sorry. Yeah, I'm doing it right. Wait. It can be 3 comma 5. It can be 4 comma 4. It can be 5 comma 3. It can again be 6 comma 2. So it could have all these possibilities. So for each of these, we'll have a probability of 1 by 6. So P is equal to 1 by 6. So it follows a binomial distribution. So X follows binomial distribution with N is equal to 1200 and P is equal to 1 by 6. So now what should we do with this? Find normal approximation to P of 90 X less than 110. So E of X is equal to NP. So it's equal to 1200 into 1 by 6. This is equal to 200. And your variance of X is equal to NP into 1 minus P. So you'll have 200 into sorry, no, wait, you'll have 1200 into P is 1 by 6. 1 minus P is 5 by 6. So you'll have 200 into 5 by 6. What is that? Let me just. 200 into 5 by 6. 166. So 166.667. So you have these. So now when you write this, you have to write. So basically x. So for a binomial distribution, like when you approximate it to a normal distribution, so you'll have x plus continuity correction minus NP divided by a variance. Variance is basically square root of NP into 1 minus P. We already calculated this here. So x 90 plus 0.5 minus NP is 200 divided by square root of variance is 166.667. And then you write this other term 110. 110 plus 0.5 minus 200 by square root of 166.667. Now if you solve for this, you will have let me just solve this. 200 minus 90, no, 90.5. So you'll have minus 109.5 divided by square root of 166.67. 110.5 minus 89.5 divided by square root of 166.67. So you'll have, what is this? P of minus you have P of minus 8.481. So now you just have to apply this. In R, you write P norm upper limit minus lower limit, right? P norm of 6.9 minus 6.93 minus P norm of minus 8.481. Let me do this. P norm yeah, you just do this, whatever answer you get should be the answer. This is how you solve it, basically. You can work it out. Okay, let's move on to the okay, the screen issue sorted. Yeah, that's good. Okay, so the next question. Consider the amount of coffee dispensed by a coffee machine to be a random variable. The coffee machine dispenses an average of 100 ml coffee with a standard deviation of 16 ml. Find the probability that the average coffee dispensed in a random sample of size is at least 105. At least means greater than equal to 105 ml. So because it is random sample, so you have to denote it as x bar. It's randomly sampled. So you need to calculate x bar greater than 105. So what did we see about a normal distribution for randomly sampled variables? So we saw that for randomly sampled random variables, it follows a normal distribution mu comma sigma square by n. It's not mu comma sigma square. This is wrong. For randomly sampled, it has to be this. So yeah, we have n, this n is equal to 64. It is given the question. Yeah, so let's calculate this. So we'll have P of x bar minus mu by sigma by root n. This is the z approximation for this. This should be greater than or equal to, so x bar greater than 105 minus mu is equal to 100 divided by sigma by root n. Sigma is 16 divided by root of 64. Root n is equal to root of 64 is equal to 8. So you write 8 here. So if you solve this, you'll have P of z greater than, if you solve this, you'll have 5 by 2. Yeah, you'll have 5 by 2. So this follows a standard normal distribution. So you can calculate this in R. P norm 5 by 2 is basically 2.5, comma. Because we have greater than sign, you write lower tail is equal to false. Now if you solve this, you'll get an answer of 0.006. Yep. So this is how you go about this kind of question. You randomly sample something and you approximate it to a normal distribution. Insurance company, just checking. Let's see chat. An insurance company has 10,000 policy holders. So this is basically many policy holders. We have X1, X2, X3, etc., Xn. We have n number of policy holders. So if the yearly claim of a policy holder is a random variable with a mean of 180 and standard deviation of 16,000, approximate the probability that the total yearly claim exceeds 4.8 million. Total claim means you have to do a summation of all this. So total claim, summation of xi. So this follows a normal distribution. So because here we have multiple random variables, this should follow distribution n mu, comma, n sigma square. So usually a normal distribution is mu, comma, sigma square. But here we have n number of people. So this would follow n mu, comma, n sigma square. So that's what you have written here. So from the question, we have n mu is equal to n 10,000. N is 10,000. 10, 1, 2, 3, 10,000 into mu is 180. 180. So you'll have 180, 1, 2, 3, 4 zeros. So we have n mu, and then now n sigma square is equal to 10,000 into, what is sigma square? Hey, this just follow the n sigma. Yeah. So into 1,000, 16,000 is equal to 16123 zeros. No, wait, I'm doing something wrong. Oh yeah, this should follow, like, this has to be square root of n sigma. Yeah. So this would be equal to square root of 10,000 into your sigma standard deviation is 16,000. So you'll just have 100 into 16,000 is equal to 160,000, 5 zeros. Okay, now what do we need to calculate? We need to calculate x bar, the summation of xi. It has to be greater than 4.8 million. So million has 6 zeros, so 10 power 6. So 4.8 into 10 power 6. So basically P of x bar 4, 8, 1, 2, 3, 4, 5. So let's approximate this. P of minus mu, like n mu is 180.1234 zeros by 100 into 16,000. This has to be greater than 481 minus mu 1234 divided by. So if you solve this, you'll have something like 30. So you'll have P of, this is basically Z. So P of Z greater than, you'll have 30 by 16. So you just have to write P norm 30 by 16 lower tail is equal to false. False because you have a greater than sign. Let me solve it. P norm. So if you solve this, you'll get 0.030. So this gives you 0.030. So this is your correct answer. Yeah, you just need to apply the right approximation. This correct formula you have to write. So here the keywords is because you have a summation. You have many n number of people. So that's why you apply this formula. Whereas in the previous question, here you had random sample. So that's why you applied this approximation. Here it's just a binomial distribution. So we already know binomial to normal approximation. This was the formula. Yeah. So you just have to look at these keywords and then you'll know which of these you have to apply. Okay. So next one, the ideal size. Just a second. Okay. The ideal size of a first year class at a particular college is 150 students. The college, known from past experience on an average, only 30% of those accepted admission will attend the class. Probability is 30% is equal to 0.3. So let X be the number of students who attend. students. Wait, the college known for past experience will actually attend uses a policy of approving the application of 450 students. So n is equal to 450. So from past experience, they have this in like they have n 450 and p 30%. Compute the probability that more than 150 first year students attend the class. So you just need to calculate this for a binomial distribution. Binomial NP 450.3. Okay, now let's just do this normal approximation of this. So you'll have probability of x plus the correction factor, the continuity correction, minus NP by variance, square root of NP into 1 minus P. So this has to be greater than 150 plus 0.5 minus 450 into 0.3. 450, 0.3 divided by square root of 450 into 0.3 into 1 minus 0.3. So you'll have P of Z greater than 150.5 minus, what is 450 into 0.3 into 0.3, 135 divided by NP. So you'll okay, solving this, you'll get square root of 94.0. What do you get? So 150.5 minus 135 divided by 9.721. So yeah, if you solve this, you'll have P of Z greater than 1.6. So if you apply P norm 1.6, lower dot tail is equal to false, you will get an answer 0.06. Yeah, so option A is your answer. Okay, that's it for this problem. And okay, next one. Okay, sorry, the answer is highlighted. Okay, anyway. Suppose T is calculated from the sample values x1, x2 up to xn to estimate theta. Which of the following is a statistic? So by the definition of a statistic, so statistic is basically any operation done on a random variable with no unknown estimates. So basically in the options given, here you can see theta is unknown. Theta is some unknown parameter. No unknown parameter. In option B is also, we have theta, which is unknown. C also theta is unknown. But option D, there is no unknown. So X is given in your question. X1, X2, X3, all these values will be given. So yeah, when you do a summation of this X to the power 3 by 2, you will be able to calculate it. There is no unknown parameter here. So the answer is option D. So this is just some theoretical question. Okay. Now let x1, x2, xn be a random sample from a probability density function. PDF is given by e power minus x minus lambda for x is greater than, this is not lambda, what is this? Delta. So this is the PDF. Determine which of the statement is true for sample mean about its bias. So sample mean, we need to calculate the expectation of x. Expectation of x. So if expectation of x is equal to mu, this means that it is unbiased. But if we have something other, if expectation of x is not equal to mu, sample mean is a biased estimator of delta. So let's first calculate that. We know the PDF. So expectation of xi can be written as delta to x. So x can be any up to infinity. So delta to infinity. What is your PDF? So you always apply the random variable x into its probability distribution, which is e power minus x minus delta dx. Now let's consider, just for simplification purposes, let's keep y is equal to x minus delta. Let y is equal to x minus delta. So now if we substitute this into this, what will happen? E of xi is equal to so you'll have, here you have x. So x is equal to y plus delta. Like from this, x is equal to y plus delta. Y plus delta e power minus y, because y is equal to x minus delta. Now you write it in terms of dy. Now this becomes 0 to infinity. Now we can split this integral into two. 0 to infinity. You can have y e power minus y dy plus this delta term. Delta is a constant. So delta 0 to infinity e power minus y dy. So if we apply this e power infinity here.
Ma'am, how limits are changed here? 0 to infinity.
So yeah, when you have things of the sort, we already had delta to infinity. So here we're just considering that this delta could be anything between 0 to infinity.
Okay.
So it's just for simplification purposes, because we don't know the value of delta here. We are assuming
Okay.
delta can be anything between 0 and infinity. So we are keeping it like that. So yeah, if we apply this integral here, e power, this will become 1 plus delta into, when you integrate this, what happens? Minus e power minus y, 0 to infinity. You'll have 1 plus delta into e power infinity is 0 minus minus e power 0 is 1. So you'll just have 1 plus, this term is actually plus 1. So you'll just have 1 plus delta. So this 1 plus delta is not equal to delta. or it is not equal to your sample mean. So this means that there is some bias. This is not equal to delta. So sample mean is a biased estimator of delta. So ideally, you should have got E of xi is equal to delta. If you got this, it would have been unbiased estimator. But what did you get? You got 1 plus delta. So it is a biased estimator. Yeah, this solves this question. Okay, let x1, x2 up to xn be a random sample from a population with any probability density function with population mean and variance. Consider the sample variance as an estimator of this. So remember earlier we saw some equations about S square and sigma like mean. So here we just need to see if the question is S square an estimator of sigma square. So how will you know this? If expectation of S square is equal to sigma square, this means that S square is an unbiased estimator for sigma square. If E of expectation of S square is not equal to sigma square, this means that S square is a biased estimator of sigma square. So you just need to remember these. And yeah, let's now solve this. So now what do we need to do? We need to basically calculate this expectation of S square. S square ka formula is given here. So S square is equal to 1 by n minus 1 summation of xi minus x bar the whole square. So this is S square. Now okay, just expectation of S square is equal to expectation of 1 by n minus 1 summation I to n xi minus x bar whole square. So this can also be written as 1. This 1 by n minus 1 is some constant. So you bring it out. Some summation of I to n expectation of xi minus x bar square. Expectation of. So now, if you remember, like in theory, we have seen that this 1 by n minus 1 stays as such. So we have seen that summation of expectation of x minus x bar. No, sorry, not summation. Summation stays as such. But yeah, we have learned that this is the variance. So what is variance? Variance is basically deviation from your mean. So x is your actual value minus your mean, sample mean. So this deviation is your variance. So this whole thing can be replaced by variance of xi. We have I to n. So variance of xi is equal to sigma square, right? Variance of any x is x sigma square because we have n samples. Let's say n is equal to 3. So what will you have? You'll basically have sigma square plus sigma square plus sigma square. So this is equal to 3 sigma square. So for n, you will have summation of sigma square would be n sigma square, right? So this will become n sigma square divided by n minus 1. Okay, you'll have this. So now if you think about a large sample, like for a population, if you consider, let's say you have 1,000, 10,000 samples. So what will happen? 10,000 divided by 10,000 minus 1 is just 999. So what is 1,000? Not 10, 9,999. So what is 10,000 divided by 9,999? So it's equal to 1.00001. So like, yeah, for any large n by n minus 1 is approximately equal to 1. This term is approximately 1. So this whole term, it just becomes equal to sigma square. So expectation of s square is equal to sigma square. So what does this mean? Sigma square is an unbiased estimator of sigma square. So yeah, option A is the answer. Yeah, it's just simple. If you go through the steps, you understand. Was that clear? Yeah, I hope that was clear. In that case, we'll move on to the next question. It's also similar, but here they've just given different value of s. So in the last question, s square was 1 by n minus 1, right? But here it's 1 by n, x minus x square. So we need to see if s square is unbiased or is it biased? And if it is biased, what is the bias? Let's try to do that. Expectation of s square is equal to expectation of 1 by n summation of I to n xi minus x bar the whole square. Now what you can do here is, wait, the random sample. So in a randomly sampled population, E of x bar is equal to mu and variance of x bar is equal to sigma square by n in any randomly sampled distribution. Yeah, let's just keep this in mind. And here what we can do is, this term here, yeah, this term xi minus x bar the whole square, it can be expanded. So it's like you have you have a minus b the whole square. No, let's not do that. Yeah, let's expand it in terms of mu. So in that case, what will you do? Xi minus mu plus mu minus x bar the whole square. You just add these two terms here. So this, you can split this equation. So you can have this as a, this is b. So a plus b the whole square. So you'll have a square plus 2ab plus b square. Now let's take the expectation of each of these terms. So expectation of xi minus x bar the whole square is equal to expectation of xi minus mu the whole square plus 2 into expectation of xi minus mu into mu minus x bar plus expectation of mu minus x bar the whole square. Now, again, this term here is variance of xi plus this term will be written as such. 2 expectation of xi minus mu minus x bar plus, now this can be written as variance of x bar. So this was variance of xi because this xi minus mu, and this is variance of x bar. Now, so variance of xi, we know it is sigma square. And this term stays. Okay, let's just. No, what we can do here is, you could also write this as 2e xi minus mu into minus of x bar minus mu, right? So this minus comes out in that case. So sigma square minus 2e of, you'll have, so basically you will have something like, yeah, you'll have a square of this term. So like if you have expectation of this, so you'll basically have 2 into variance of x bar, because yeah. And the third term is variance of x bar. We don't know this because it is a randomly sampled variance. We keep it as such. We don't know this either. It's randomly sampled. So we have these two terms. If you look at, you have minus 2 into variance of x bar plus variance of x bar. So what does this become? It becomes sigma square minus variance of x bar, right? So if you remember, for randomly sampled population, variance of x bar is equal to sigma square by n. So we have sigma square minus sigma square by n. So if you look at this, now what do we have? Let's go back to the previous slide. Expectation of s square is equal to sigma square minus sigma square by n. So now this is your sample variance is equal to population variance minus bias. Like it's plus some bias, but in this case our bias is negative. So bias is equal to minus sigma square by n. So S is a bias estimator of sigma square and its bias is minus sigma square by n. So this. So option B is the correct answer. So this is just basically like a derivation. So yeah, whenever you look at the question, you see S has 1 by n. So in that case, this equation will hold. But when this equation of S has n minus 1 in the denominator, you will have expectation of S square is equal to variance square. Yeah, we just derived these two. And yeah, this, if you remember, it will be easier. Was that clear?
Ma'am, please explain the last step.
Last step. This one you mean?
No, ma'am. From when you take ma'am, second last. Ma'am, yes,
Yeah,
this
yeah.
slide say.
Let me add a slide.
Yes, ma'am. Same slide. Yes, ma'am. This
Yeah,
slide.
yeah. So this step you mean, right? Like how did we get from this? How did we get this?
Yes, ma'am.
We had 2 into expectation of xi minus mu into mu minus x bar. 2 stays as
Okay.
that. And let's have this expectation. So we have xi minus mu first term. Second term, you just reverse the minus sign. Now what
Okay.
was x bar minus mu? This minus sign goes out because
Okay.
yeah. No. And now what you have is you have like randomly sampled and one this. So when you
Okay.
have both of these, it's basically something equal to e of x bar minus mu the whole square. So again, when
Okay.
you have something, it is this one e of x bar the whole square is equal to variance of x bar. So that's why you
Okay.
have minus 2 variance of x bar. So that's what we applied here. Minus 2.
Okay, ma'am. Got it.
Yeah. And then yeah, you solve this. Variance of x bar, you know this, you substitute. You get it.
Okay.
Okay, this one, let x1 and x2 be independent random variables with mean mu and variance sigma square. Now we have two estimators. We have mu1 hat. Like theta is some estimate, theta hat is an estimate. So when you have multiple estimates, you have theta 1 hat, theta 2 hat. So in this case, theta is mu. So you have mu1 hat is equal to x1 plus x2 by 2. Mu2 hat is equal to x1 plus 3x2 by 4. So you want to see if mu1 hat, mu2 hat are estimators of mu. Mu hat, estimator of mu. This is the question. So how do you do it? You need to basically do, what is this called? Expectation of mu1 hat. So expectation of mu1 hat, it's basically expectation of x1 plus expectation of x2 divided by 2, because we have x1 plus x2 by 2. Expectation of x1, expectation of x2 divided by 2. So expectation of x1 is mu. Expectation of x2 is also some mu. So you have mu plus mu, 2 mu, 2 mu by 2. So this is equal to mu. So mu1 hat is mu. So mu1 hat is an unbiased estimator of mu. Now let's look at mu2 hat. Expectation of mu2 hat is equal to expectation of x1 plus expectation of plus 3 into expectation of x2 divided by 4. Am I doing it right? Yeah. So you will basically have mu plus 3 mu divided by 4. So this is equal to 4 mu divided by 4. This is again equal to mu. So both expectation of mu1 hat and expectation of mu2 hat is equal to mu. So both are unbiased estimators. So it could be either option A or B. Now we need to see if, we need to see which of these holds. We need to see if variance of mu2 hat is less than variance of mu1 hat, or variance of mu1 hat is lesser. We have to do that. For that, what do we do? So variance of mu1 hat is equal to variance of x1 plus x2 by 2. This was the question. So when you have a constant in variance, what do? You bring it out and take a square of it. So you have 1 by 2 square. So 1 by 4. Variance of x1 plus variance of x2. So you will have sigma square plus sigma square by 4 is equal to 2 sigma square by 4 is equal to sigma square by 2. So variance of mu1 hat is equal to sigma square by 2. Now similarly calculate variance of mu2 hat. So variance of what was mu2? x1 plus 3x2 by 4. So when you bring this out, it will become 1 by 16. Variance of x1 plus 3 into variance of x2. So this will give you 1 by 16 into sigma square plus 3 into sigma square. So this gives you 4 sigma square by 16. So sigma square by 4. So variance of mu2 hat is equal to sigma square by 4. So obviously, what is this? V2 is smaller than V1, right? Because it has larger denominator, V2 is smaller than V1. So option A is the correct answer. Variance of mu hat 2 is less than variance of mu hat 1. Option A. Okay. Yeah. Let us go to the next question. So let x1, x2 up to xn be a random sample from a population with normal distribution. Summation of xi follows a normal distribution, mu comma sigma square. But yeah, we have multiple variables, summation x1. So this will follow a normal distribution, mu comma sigma square by n. Assume sigma square to be known and let x bar is equal to this. So we need to find what value of this will give us unbiased mu square. So the output should be mu square, but what input? So basically we have this, this is known, expectation of sigma. So mu square, so let's take expectation of sigma square. So yeah, this is something you need to remember. Expectation of x bar square is equal to variance of x bar plus expectation of x bar the whole square. Now we know these values. Variance of x bar is equal to sigma square by n. And expectation of x bar is mu. So mu the whole square is mu square. So now what do we have? We have sigma square sigma square n. So we only need mu square on the left hand side. On the right hand side, you only need mu square on the right hand side. So you bring these to the other side of the equation. So expectation of x bar square minus sigma square by n. This will give us mu square. Now this was a question mark, right? This term, what is it? X bar square minus sigma square by n. So that is our answer, x bar minus sigma square by n. So this is an unbiased estimator of mu square.
Ma'am, what else if in bias estimator of mu square there is some constant also, like uh, a mu square, b mu square, like this.
A mu square.
Means there is some constant also.
Yeah, you can just like multiply the constant on this side. So in that case, this you would want this to be on your right hand side. In case this one doesn't have that constant, you just multiply this left hand side term with that
Mm.
constant.
Means
You will
by
have,
x bar square.
yeah.
Uh,
So you'll basically have like constant into, or you can put the constant inside also. Like it will basically be that constant x bar square minus constant into sigma square by n is equal to constant mu square.
ma'am, means with both the values
Yes,
of
yes. Because
okay, okay,
constant is common to
okay,
any term that is inside the bracket. So when you
okay.
have two terms inside the bracket, the constant applies to both terms.
Both the terms. Okay.
Yeah.
Thank you, ma'am. Thank you.
Okay, what is this? This is also something very similar. Oh, no. Okay, I highlight for the answer. Okay, anyway. Suppose we have a sample of size 3n from a population of X with mu and variance is given. Suppose there are two estimators. Mm, oh, easy way to calculate. Okay. So it's very similar to the problem that we saw earlier, the previous one. So we need to calculate expectation of mu1 hat, mu2 hat, and then variance of mu1 hat, mu2 hat. So first, mu1 hat expectation is equal to expectation of 1 by 3n summation 3n I to 3n expectation of xi. So expectation of xi is mu. So 3n mu. So when you multiply this into mu, what will come? 1 by 3n into 3n mu. So it will get cancelled. So expectation of mu hat 1 is equal to just mu. So mu1 hat is unbiased. Now let's look at mu2 hat is equal to, what is mu2 hat? 1 by 2n. You have summation 2n x1, xi. So you'll have 2n mu. Again cancel. This also you get mu. So both mu1 and mu2 are unbiased estimators. Both mu1 and mu2 hat are unbiased estimators. So it could be A or B. And now you need to calculate which variance is lower. So variance of mu1 hat is equal to, you have 1 by 3n. So that constant becomes square. 1 by 9n square into summation of I to 3n variance of xi. So you'll have 3n sigma square by 9n square. So you'll have sigma square by 3n. So this is your variance of mu1 hat. Now variance of mu2 hat is equal to 1 by, you have 2n. So that becomes 4n square. Summation I to 3n, I to 2n variance of xi. So you'll have 2n sigma square divided by 4n square. So you'll have sigma square by 2n. Right? Yeah. So now in this case, you have this, you have this. So now V1 is smaller than V2. If you look at this, because V1 has a higher denominator. So V1 is small, becomes smaller than V2. So what holds V1? So option B is your correct answer. So we saw two problems which follow the same steps. So this problem and another problem that we saw. Yeah, this and not this. This one. So you calculate expectation variance and you see. Yep, that is it. Now moving on to the next one. So we have this. A computer software package was used to calculate some numerical summaries of the data. The results are displayed. Variable is x, n is 100, mean is 50. So standard deviation is 2. So variance is basically standard deviation squared. So variance is 4. 2 square is equal to 4. So it could be option C or D. Now standard error. So what is standard error? It's square root of s square by n, or it's square root of sigma square by n. So sigma square four divided by what is n? 100. Square root of 4 by no. What? So you'll have 2 by 10. Wait, let me just make it. How do I erase this? Yeah, this is equal to this. So when you take square root, you'll have 2 by 10 because 2 square is 4, 10 square is 100. So when you solve for this, you'll have
Excuse me,
1 by
madam.
5. Yes,
Madam. Here variable n is equal to 100, no, madam. It is pertaining to the number of that is the population, no, madam, capital N.
yes,
But you are, yeah, so but you are taking sigma square by n. Sigma square is for the variance of population, and the s square is for population of sample. Sorry, sample variance.
yes.
So how can we apply this formula? Like,
So they're not saying which is
should,
sampled from which. They've just given like general stats. So the n,
okay.
this is
Okay.
capital and small. In this case, like anything holds. Yeah. So n is 100, standard deviation, and your variance is 4. So you can just directly apply this. Yes.
Okay, ma'am.
Yeah, so you get standard error 1 by 5. So variance also you get 4. So this. Yeah. You just check if this answer is correct, just in case. What is the answer? Yeah, this is the correct answer. Yeah, this is how we apply it. You use this formula and these values. Yeah, then this is it. And then we have one final question, like about Kramer-Rao lower bound. Like how do you calculate that? So let x1, x2, x3, xn be a random sample following Bernoulli's distribution. So we need to find this x bar the best unbiased estimator of P. And does it attain the Kramer-Rao lower bound? So let's first calculate expectation of x bar. So x bar it follows a Bernoulli distribution. So basically Bernoulli distribution is like summation of x1, x2, x3 to xn. So you'll have one n I is equal to 1 to p, and probability will be p. So when you apply this, you'll have np divided by n. So you have p. So yeah, because you're getting expectation of x bar is equal to p, it is an unbiased. So x bar is an unbiased estimator of p that holds. And then we need to see, does it attain the Kramer-Rao lower bound? So how do we know this? So variance of x bar, if variance of x bar is greater than or equal to CRLB, it is satisfied. So for this, we need to calculate variance of x bar. And no, yeah, we need to calculate variance of x bar and we need to calculate this one. So calculating this would be simple, the usual steps. Variance of x bar is is equal to, so you'll have this thing 1 by n. N is a constant, so constant bringing out, you square it, 1 by n square, variance of xi I to n. So basically, what is your variance in your Bernoulli distribution? 1 by n square you'll have as such. And then, yeah, so this would be np into 1 minus p. So this is your variance for Bernoulli divided by, oh, we already have this n square. So this gives us p into 1 minus p divided by n. So this is your variance of x bar. Now let's calculate CRLB, Trimmer-Rao lower bound. And to do that, first we need to calculate information of P, the Fisher information. Fisher information of P. So how do you do that? So it can be E of, it has to be del, like partial differential theta log f of x given theta, the whole square given P. And further, you do a double differentiation. Log of f of x given theta. Okay, let's try to solve this. So because xi follows Bernoulli's, right? Yeah, follows Bernoulli's distribution C. So if probability is equal to 1, you'll have a success. And if probability is 0, you'll have a failure, which is 1 minus p. So yeah, from that we can calculate f of x given p. So here basically theta is your p. X given p is equal to, we know the function p of x, p power x, 1 minus p into 1 minus p power 1 minus x. So x is the number of trials. So xth trial would be a success and 1 minus x will be your no failures. So you have this. Now you just apply log on both sides. So log of f of x given p is equal to, you apply a log here. What will happen? When you apply log of p power x, you will have, this one will come here. So x log of p plus 1 minus x log of 1 minus p. So now you differentiate on both sides. You do a partial differentiation. Delta p log of f of x given p is equal to, so if you remember, no, yeah. So you just need to remember this, like when you have, what do you have here? So x constant, x stays as such. So when you differentiate log p, it will become 1 by p. So you'll have x by p plus constant stays. And then when you differentiate log 1 minus p, this 1 minus p will go to the denominator, 1 minus p. So this is your single different partial differentiation of this. You have this value. Next, again you do a differential on that. Now you do double differential. Delta square by delta square p log of f of x given p is equal to, you do again you do a differential on this value. You have x by p minus 1 minus x by 1 minus p. And y. So now when you differentiate 1 by p, you will get minus 1 by p square. And here also you will have 1 minus x by 1 minus p the whole square. The square. And this is a double differential. Now you need now with this we calculate information of p. So you'll have minus n e of double differential log f of x given p. So this is equal to minus n e of, you just write this minus x by p square minus 1 minus x by 1 minus p square. So this will give us minus n. Just replace the x with p because, yeah, no. You have okay, when you solve this, what will you get? You will have n, wait, minus p minus 1 plus 1. So you'll have minus 1. You already have minus n. Minus 1 in numerator divided by, wait, I'm not doing it wrong. So if you solve this, you'll have n by p into 1 minus p. So now you can see that okay, there's one more step. So we calculated the Fisher information n by p into 1 minus p. Now we have a function of theta that is equal to p, the probability function p. And now when you take a differential of p, like differential of g in terms of p, like theta is p here. So p the whole square. So when you differentiate like p, it will become 1. So g square is also equal to 1. So now CRLB formula is equal to g prime theta divided by information of theta. So now this is equal to 1 divided by n by p into 1 minus p. So this will be equal to p into 1 minus p divided by n. So now you can see that CRLB is equal to this. And if you remember, the variance was also equal to this value. So now CRLB. So CRLB has to be lesser than or equal to your variance of x. But here it is equal to. So it is satisfied. So here Rao lower bound is achieved. Yeah, just to give a recap, you have you write the PDF. So how do you calculate this? Wait, you calculate the expectation and you calculate variance of x as usual. You have this value. And then to calculate Rao lower bound, you write your PDF, which is like f of x given theta, x given theta. Step 2, you take log. So you'll have log of f of x given theta. Third step, you do a differential log of and then step 4, double differential. And then we calculate the information, Fisher information, which is equal to minus NE double differential of your log f of x, x by theta. You have this. And then step 6, you have the probability function, which is g. And then you differentiate that. That gives you g prime square. So you need to calculate this. And finally, CRLB is equal to your g prime theta square divided by information of theta. So this gives you the CRLB value, and you have to compare. So CRLB has to satisfy this. Yeah, so if it satisfies this, it means that this P is a good estimate for this. So yeah, it means that this X bar is a unbiased estimate, and also it's an efficient estimate because it satisfies this CRLB. Yeah, so that's it. Yeah, these are all the problems. Oh, was that clear?
Ma'am, ma'am,
Mm-hmm. Yeah, just one by
ma'am,
one.
please could you help me out with the question number 14 and 15 in assignment 10? How should we proceed for that? Assignment 10.
Yeah, I am not supposed to discuss it, but yeah, let me just look at the question and see.
Yes, ma'am, please suggest how to do that. I just want
Mm, 10 assignment. Okay, yeah, just
a
give.
little help on the last two questions.
It's just basically have to do the same thing. Like you have to take a log. But yeah, you can just Google like how do you take a log of this term? Well, sorry, log, like log and a differential. Yeah, in both the cases,
Ma'am, my question that I have to proceed in the way that you just told me the last question,
yes,
or it just with other method.
you have to
Because
do the same way. That method stays.
Fisher,
But for Fisher
uh,
information, it's enough you just calculate this I value.
which part?
Yeah, to calculate I, you basically need to do all of these. So if you want to calculate I, you need
Hmm.
to start from, yeah, so I formula is this.
From this part, I have to
No,
start
like,
this question.
but to derive at this part, you need to
Mhm.
calculate log also. So where did I do it? It disappeared. So wait.
Because I'm finding it difficult because
Yeah. So
uh,
hmm, yeah.
because I'm not getting how to proceed with such question.
Okay. Hmm,
From which part I have to start with?
yeah. Just give me a minute.
Just provide me some hint so that I can mm, proceed with this question.
What is your function? We have f of x theta x minus 1 is 0 to 1, theta is 0 to infinity. You have these, right? Now what you should do is first you should take a ln of this, logarithm of this. So first logarithm of theta, am I writing it wrong? Is it subscript? No, it's not subscript, it's just theta into x. Wait, just this is superscript. X power theta minus 1. You have to take a log of this. You can Google or you can use online calculators because you're not expected to know all this. But yeah, yeah, I just have to take a log of this. And then what you do after you do this, whatever answer you get, you differentiate it in terms of theta.
Okay.
Log of like whatever answer you get here, you differentiate this. And here you'll get another answer. So now again you differentiate this answer in terms of theta. So now you have done the differentiation twice. So this step is actually your double differentiation of this term. Log of f of x. Okay, you first take a log of this, differentiate it with respect to theta, and whatever answer you get, you again differentiate it with respect to theta. And then what do you do? Just after you differentiate it, yeah, so you are at this step now. You have this value. You have differentiated twice, so you have this value. Now you just take the expectation of whatever value you get. How do you do that? So minus n expectation of your double differential. So like in previous lectures, all for expectation, you need to integrate over the limit, right? So minus n. So for calculating expectation, you need to do some integration. So x in terms of x. So you need to integrate this over 0 to 1. If yeah. Yep, that's what you want to do. You integrate it, you'll get some answer. So that is basically your Fisher information. So I think the answer you'll get, it'll follow the format. It'll follow something that looks like this formula here. It will look like something of this format. So from this, you can just know what is the answer. Mhm. Yeah, then this is how you should do it. And next problems also. Basically the same thing you have to do. So the 15th question, you have to actually calculate CRLB greater than or equal to. So if you calculate the CRLB, you'll get some value. So that value is your answer. So CRLB value you'll get by divided by. So for normal distribution, population variance, random sample. So you'll have sigma.
Ma'am, CRLB of which quantity we have to find out, because
So you have to
uh,
follow X
hmm,
bar randomly sampled sum. So you'll have sigma square root and something you'll have sigma. So when you randomly sample, you have to write sigma square by n. And then because
hmm.
the quantities, where is it? In sigma. Yeah, I think it's basically in terms of sigma square by n. So you'll get some value. Wait, let me just have check at this. I'll see if I have the solution. Like I'll just see if I have the answer key to it.
Can you provide some hint for question number 10 of assignment 10?
Question number 10. Yeah, this was pretty simple. This is the thing we already saw. We discussed a very similar two questions. Yeah, that is very much straightforward. So you just need to calculate the expectation of mu1 and mu2 hat, and then you need to calculate variance 1 and variance 2 hat.
I joined late, so could you please show the previous question for that?
Yeah, but before that, let me just have a look at this question 15, if that's okay. But yeah, let me keep that slide on. You could have a look.
Madam, tomorrow, excuse me, madam.
Yes.
Madam, tomorrow morning by 8 o'clock, can we get this video
Yeah.
uploaded? Hello?
Yes, yeah, you get it tomorrow, 8 o'clock.
No problem.
Yeah, so question 15, right? It follows a normal distribution. So, if you remember week 9's lecture, we saw not bivariate, right? It'll just follow normal. Yeah, wait. You need to have like your f of x actually would be this normal distribution equation. Sigma square, like whatever that is, e power of, do I have some more? Yeah, you remember this, right? E power minus summation of xi minus mu by 2 sigma. So yeah, you have to start with this for your 15th question. You have to take a ln of this, logarithm of this, and then you have to differentiate over this, and then again differentiate. Yeah, so that's what you have to do. Yeah, it's a bit complicated. Yeah, I don't think you'll be given such complicated questions in your exam.
Ma'am, it means we have to do double integration of this value
Yes.
fx.
Yes.
Mhm.
In terms of sigma.
Okay.
Yeah, you have to integrate it in terms of sigma because this is your parameter that we need to estimate.
Okay.
Yeah. So you have to differentiate over sigma square.
Oh, okay, ma'am. फिर after that we have to take logs and proceed. Uh,
This is the standard step. So
okay.
of x we define whatever that is, take a log, differentiate it
Hmm.
once, and again that answer you differentiate, and then do an expectation of that. Expectation is basically integrating over some interval.
Okay.
Yeah, you do that, and then G prime.
Bit complicated question, ma'am.
Very complicated.
Okay, ma'am. Thank you.
Ma'am, could you provide some hint for question number 10?
Getting back to it. We saw two questions related to that. Yeah, this is, wait, what is the question? Did I actually solve the question? No, yeah, this is a different question, but similar format. You could see the slide, right? Yeah. So you have mu1, mu2 you have. Mu1 is x1 plus x2 by 2. So now you need to calculate expectation of mu1. So expectation of mu1 would be, you have two terms. So expectation of x1 plus expectation of x2 divided by 2. So we know that expectation of x is equal to mu. So you'll have mu plus mu is equal to 2 mu divided by 2. This is equal to mu. So you're getting expectation of mu1 hat is equal to mu. So which means this is an unbiased estimator of mu. And if you do the same thing with mu2, x1 plus 3x2 divided by 4, you'll have expectation of x1 is equal to mu, and 3 into expectation of x2 is equal to 3 mu. If you add it up, 3 mu plus 1, 3 mu plus mu is equal to 4 mu by 4, because denominator we already have a 4. So this gives us mu. So both of these gives mu. So this means that both mu1 hat and mu2 hat are unbiased estimators of mu. So now the answer could be option A or B. So the second step, you need to calculate variance of mu1 and variance of mu2. And you need to see which one is lower. And you have to answer it accordingly. If variance of 2 is lower, this option A is correct. If variance of mu1 is lower, option B is correct. So in this question, yeah, we see how we solve it. Same thing. So variance of x1 plus x2 divided by 2. So denominator, we have a constant. So when you bring out a constant out of a variance, it becomes a square. So it becomes 1 by 2 square into variance of x1 plus variance of x2. So 1 by 4. So variance of x1 is sigma square. Variance of x2 is also sigma square. So 2 sigma square divided by 4. So now, if you solve this, your variance of mu1 hat is equal to sigma square divided by 2. Now, similar way, you solve variance of mu2 hat. If you do the same thing, you get variance of mu2 is equal to sigma square divided by 4. If you look at both of these, variance of 2 is smaller because variance of 2 has a bigger denominator. So this overall value would be small. So V2 is smaller than V1. So V2 is smaller than V1. Option A is your answer. Yeah, that's it. This is how we solve it.
Thank you, ma'am.
Yeah, if you want, I could upload it now, like in the recording, but it'll take time. Yeah, I'll see how long it takes. I'll try uploading it now, but otherwise, yeah, you should have it 8 o'clock in the morning. Is that okay?
Okay, ma'am.
Okay. How do I stop sharing? Okay. Yep. And see you next week, next Tuesday. Like if you have any problem, we could discuss further. Yeah, we could try solving these complicated ones next week.
Okay, ma'am.
Okay. Thank you.
Thank you for the session.
Right.